if they miss it, they won't be caught in a difficult situation. And that is a little bit of reflection on what we saw yesterday. So yesterday I introduced a perspective on modeling, which is a broader one than you'll hear in some quarters. And it reflects the fact that we model for many reasons. One of the reasons, and certainly the most prominent one if you look at the literature these days, is the use of modeling for quantitative policy analysis, to try to advise on the choice of different intervention strategies, screening procedures, prophylactic measures, or outbreak response measures. And that's certainly a very, very important use of models. It's one that captures a lot of attention and where there's a lot of draw these days from decision makers at different levels of authority. And yet, we model for many reasons beyond that. If you go to the work of Don Burke or Josh Epstein, Don at Penn and Epstein at Hopkins, they've enumerated dozens of reasons why we model, and I won't try to duplicate their list here, except to remark that models come in very different shapes, sizes, forms to address different problems. And like maps, they're specific to purpose. We don't model the world in its essence. What we do is we model the essential features required to answer certain types of questions for a problem. And one of the corollaries of that is that when we model, what the model looks like depends on our questions. It's like a map. If you wanted to get through Minneapolis by car, you'd use one sort of map. If you wanted to do so via walking, you might use another that emphasizes the trails and walking paths. If you wanted to understand why there are brownouts in certain areas of Minneapolis, electricity failures, you'd use a different sort of map. And if you wanted to understand why water is collecting at certain locations and causing flooding problems, a different sort of map would be needed. They're all maps of Minneapolis, but they have different different types of components that they capture within them. So they're different abstractions. They hide different details and capture other details. Are we worried about the volume?
Just a little.
Okay, sure. I'll, we don't want to scare people on the first floor. So I'll lower that, but it seems that my voice is penetrating. Okay, is that a bit better?
She's still here, right?
Okay. So models are abstractions, and they appear different for different purposes. Some other purposes for which we might build a model very reasonably, beyond advising on policy selection, would be to build theory, to sort of understand what might be driving patterns in a population. This is a very common need, but often we reason in our head about what might be going on in a way that is more prone to mistakes, to inconsistencies in our thinking, to cognitive dissonance. And by building a quantitative model, even if it's not fully tied down yet by evidence, we can start to try to make sense of what evidence we have observed more consistently. So models can help us build theory as well as explicating the implications of theory once built. People get very caught up on, we don't have the data for this situation, so we can't model it. That's a refrain you'll hear occasionally. But there's another whole class of modelers who build models precisely to build that theory, to start to have some understanding of what may be going on out there in the world. Another use of modeling is to try to identify the key uncertainties where the data is most keenly needed. And that might be a reason you build a model up front. Even though you don't have a complete set of data, it helps through sensitivity analysis give you some sense about where the data might be most valuable to fill in first. motivate field work, might motivate literature reviews, might motivate primary data collection of other sorts, surveying, etc. Often we use models to try to identify key uncertainties. Another use of models is to try to explain trends or patterns that we see. Yet another use of model is to test study designs, to test surveillance strategies, to test statistical metrics that serve as proxies for trying to quantify underlying factors that are directly hard to measure, that serve as surrogates for those factors in our data. And we can often use models, even if they're not fully pinned down by evidence themselves, to discover gaps or inconsistencies or shortcomings of potential study designs or statistical analysis strategies for inferring things and identifying surrogates, etc. So if we're dealing with empirical data, sometimes we can use models to help identify issues with that data, vulnerabilities of that data, questions where that data needs to be challenged. And if there's interest in this, I could give some examples of how we've used models in this way. And so when we're thinking about the modeling landscape, we're talking about something where models fit in many different areas of contribution. And that it bears in mind emphasizing this, that when we see these models, it's not a one-size-fits-all. We're not trying to create for all questions only a model where only the finest data has been used. We may be using models for theory building where they're very stylized but help us think through the implications of our theory. So those models we saw yesterday had that in common. Models capture theory and evidence in one place, under one roof, and help us think through more consistently than we can in our head the implications of that theory and evidence for behavior over time. These sort of dynamic models do. And we use these dynamic models in many ways, but they have that at their essence. They have a place for theory as well as for, and knowledge related to theory as well as for data. The models we saw yesterday, we encoded in this package AnyLogic. And AnyLogic is a package I teach not because I think it's perfect, far from it. I have many critiques of AnyLogic. I could probably write a book of critiques of AnyLogic. I routinely serve as a gadfly for those who build AnyLogic by poking them about shortcomings of it. But I happen to think that for many tasks involving modeling, it's a top-notch tool. Top-notch in the sense of being the least bad of the alternatives. Winston Churchill said about democracy, it's the worst of all forms of government except for everything else. And I kind of feel that about AnyLogic. It's the worst of all modeling tools for many jobs except for everything else. One of the reasons we like it is because we tend to do our work in cross-disciplinary teams. And you may have a modeler who's doing the heavy lifting, building most of that model up from scratch, but we need people across the team to understand the model, to be able to look at it and understand something about what its assumptions are, to be able to interact with it by running it, to be able to contribute to that model by looking at it and saying you're missing this, or you need to add that, or you don't need this extra detail because that's actually just what's on the books. It's not how it actually happens. One of the liberating things about using this very visual display of AnyLogic is, besides being visually attractive and approachable by a modeler, it allows people in the team to often contribute in ways they wouldn't be able to do so. If it was just C code, or if it was code in R, or code in MATLAB, stakeholders are often not going to be able to see what's there and not going to be able to critique what's there because of that. And Kurt, in his work with our provincial ministries, ED Weights and Patient Flow Initiative, uses very powerfully in teams there to to elicit feedback from people about this model. Another feature of AnyLogic is that the fact that people from a wide variety of backgrounds, even if they can't build a model, they can run it. You could distribute a model to be run by others. And the outputs of that running can often, ladies and gentlemen, elicit understanding, observations, and empirical evidence that otherwise would go missing. It's often someone who's a stakeholder might look at a model and have contributed a limited amount in terms of, say, parameter estimates. But when they see the model running, they'll say, oh, that's a pattern we see a lot. Or wait, we've never seen this occur, where the model's estimating a caseload of a certain amount for certain bursty periods. Or they'll say, well, that's typically longer than the model depicts. So often you can elicit, by having a stakeholder run a model or observe a model while it's running and seeing the results, especially visualized results, they may spot patterns that bring extra evidence to the table from their side. They spot patterns which they dispute. They say the model isn't capturing that well, or they'll lend confidence to the model. And I want to emphasize this notion of models as learning tools, because when a model fails to align, when a stakeholder sees a model, sees results in that model that don't align with observed patterns, that's not a failure of the model in my view. It's a success of the modeling process, because what you have done is you have just identified a previously latent, a previously hidden inconsistency between our theory of the world, as captured previously in our heads, now in the model, and observed evidence. Without a model to tell us the implications of that theory over time by running the model, we wouldn't have spotted this inconsistency. The stakeholder wouldn't have spotted this inconsistency between what the model produces and observed evidence that they've seen or observed experience. But it's by virtue of running the model sometimes and seeing the results of it that those inconsistencies get discovered. And those inconsistencies, again, are not the results of a failed crystal ball, a model that's, whose usefulness is shattered because it's predicting something wrong. It's rather an opportunity to learn in the modeling process to improve that model, to improve often our understanding about how the world works, our understanding about what's likely going on out there, which is what a model captures. So, in short, models are tools for learning more quickly, more robustly, and more deeply about the world. My colleague Jeff McDonald, who some of you have enjoyed the pleasure of meeting, hirsute man from Sydney, he talks about models as learning prostheses. And it wasn't until I broke my foot last year in multiple places and sprained an ankle that I discovered what he really meant. Prostheses are tools, whether it's a cane or a crutch or a boot. They're tools that help us work within our limitations, help us extend our functionality, our ability to function within the scope of our limitations. So we have a cane to help us deal with, our bum knee. Or we'll have a set of crutches because we've got this broken foot. And models are like that. They help us deal with our limitations as people. We're not very good. We're really good at certain things and not at others. So one of the things we're not very good at is taking a theory of the world, putting it together with evidence, and being very consistent about understanding what its implications are for behavior over time. That's what a model does great at. That's what computers do great at. It's something very stupid. It's something very straightforward and methodical. It's hard for us to do in our head, but it's easy for a computer to do, to play out the implications. And it raises that opportunity for learning. So models are learning prostheses. They help complement our limitations by helping us learn from evidence more quickly and fully. You'll sometimes hear models held up as an alternative. People will sometimes say, well, there's modeling and then there's empirical evidence, and you need to balance both. I would say models help us learn from the empirical evidence more deeply, more quickly, more robustly. They help us make sense of that empirical evidence about what it tells us about what's going on in the world and spot inconsistencies. So that's a philosophy of modeling that carries through our modeling projects, and it shapes how we interact with stakeholders, and it shapes what tools we use. We want tools that are transparent, that can be understood, can be widely used, and for many problems, we find that AnyLogic is a tool of choice there. So we built up models in AnyLogic, and yesterday I reflected at the end of the day, at least at what we saw. You went through an admirable, perhaps tortuous, but admirable set of materials yesterday. I had mentioned early on that the modeling toolbox associated with agent-based modeling is much broader than that for compartmental modeling. Compartmental modeling, we have stocks and flows. We have state variables and their derivatives, depending on how you want to characterize the situation. And that's beautiful stuff. And there's certain types of analyses that are very powerful you can do with that uniquely. But when it comes to agent-based models, we have a broad variety of additional types of questions that we can answer that we can't reasonably answer with compartmental models. And yet we have a broader modeling vocabulary. And we saw many elements of that modeling vocabulary yesterday. In fact, you saw, mark my words, most elements of the AnyLogic agent-based modeling vocabulary yesterday. There'll be a few more alphabetic letters coming in, the X, Y's, and Z's, these, of the AnyLogic alphabet. But you saw a lot of it. Parameters. Parameters encode an assumption and communicate the assumption from the point of creation to the thing holding the parameter. So you put a parameter in main, and the experiment tells main what to assume about that parameter. It communicates that assumption from the experiment to main, because the experiment's responsible for creating main. If you have a parameter in an agent class, and that agent class is, there's a bunch of agents embedded in a population domain, it's the population that says what to assume about those parameter values. So we saw parameters, and we saw how they could be used to create more flexible models. And the last example could even be used to encode rules, who to vaccinate, or how, in what way to intervene upon them. But we also saw a bunch of other elements, state charts, right, with states and transitions between states, to encode not the current state of someone, but the rules that govern the evolution of that state, and under what conditions those rules apply. So we saw transitions from state A to state B. We saw a bunch of different types of transitions, did we not? Timeout transitions, which capture a certain period of time. You leave after a certain exact period of time. Stand in juxtaposition or in contrast to hazard rate-based transitions. If you have a fixed hazard, you have a certain chance per unit time that's, no matter how long you've been in that state, as long as you're still there, you have a certain chance per unit time of leaving in the next day or week, or choose your time unit. We also saw that we have these things called events that we can use to trigger either things at either one time, like at the starting time of a model, or on an ongoing basis, say at a certain rate or with a certain fixed frequency. Maybe it's reporting every week. So we, in our model, just like in the emergency rooms and in major hospitals, maybe there's reporting done weekly. And so there's an event that fires off once a week, boom, 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 boom. Or maybe we have an event that goes off on a more frequent basis, say 10 people per day who are vaccinated. And that would be a rate, a sort of hazard rate. It's firing. Every time it fires, it does something. That's how events work. They fire and do something every time. So we saw events. We also saw how we could use another way of encoding state, which is something called a variable. Do you remember we added a variable for color? Maybe I remember it because it was spelled in an American way. But it was called color, and it encoded someone's color. Remember that? That was an aspect of their state beyond just their state chart. We had sort of their color. And we'll be seeing variables soon enough, again. Ladies and gentlemen, we also incorporated yesterday, all in the span of this one day, networks. So we put people, situated them in space early on, according to their parameters, and we captured their context in a network. So context in space, context in network. And we could, in fact, make those locations in space, for example, depend on their characteristics, on their income, or on their age, if we wanted to do so. And we could have networks that are assortive, for example, because of that. Having done that, we, at the end, took a look at implementing an intervention. We had infection traveling through these networks, infecting individuals through the use of messages by which one individual communicated to another, and people would therefore there's a spread of infection, and we saw how we could implement an intervention at the end. And I went a bridge too far there, but it basically showed how we could roll out an intervention over time in the form of vaccination. So you went through a lot yesterday. I use that term advisedly. You went through a lot, but you contributed a lot. You're to be congratulated. Today will be a bit more gentle in some respects because you've already used a lot of the elements of the vocabulary. You've gotten your ABCs going, and now we're going to use them to build those muscles a little bit more and to learn a few more letters today. So, but in some ways we're building words today. We're using those basic components that you've been using, which are most of the components of the ABM vocabulary in any logic. We'll be building up things from them that are really interesting, like a hierarchical model, a model of a general environment, and then cities, and then people within cities. But it could be farms and animals within farms, and you get animals move between farms. Okay, so that's what we'll be seeing today. So that was my retrospective, and I think we'll dive into it, but I want to make sure that people can ask some questions. So are there any questions from yesterday people would like to raise or ask about? Yeah?
Not so much about yesterday per se, but
sure.
So you might cover this in the future, but discrete event modeling, I've been kind of battling between should I use agent-based or discrete events for certain things.
Okay.
I want to just how it fits into that framework.
So, right. So discrete event modeling, we're going to have a module on discrete event modeling. And per my comments yesterday, the schedule is adaptive, and if there were, my default thinking was today to use some time in the afternoon for a bit of hybrid modeling, one type of hybrid model with pathogen reservoirs. But I might alternatively do some discrete event modeling this afternoon, where we look at service delivery, and we see how that service delivery is depicted in a very crisp and powerful fashion by discrete event modeling, particularly in the context of limited resources, where you have resource-limited workflow or processing. You can capture that often very, very nicely with an economy of specification with discrete event models. And it turns out these discrete event models can be integrated with in a quite beautiful way with agent-based models. So if there were interest, is that a significant interest on your part?
Yeah.
Okay, I could weave that in today. Okay, we'll do that today, okay? We'll do that probably this afternoon. Okay, that's great. Any other questions or needs? Okay, yes?
Well, it's also kind of maybe unrelated, but for system dynamics, I know you mentioned like any logic can do
absolutely,
but I don't know if you're just doing like system dynamics for instance. Is it any logic is still like a good choice versus other software?
Yeah. So great question, Irene, and I could talk quite a bit about this. Kurt could also probably comment on this a fair bit too, because he's done some system dynamics in AnyLogic, but also, if I'm not mistaken, that work you did with TB for Dr. Hepner, was that in Benson? That was in Benson, wasn't it?
Yeah.
So Kurt has used multiple system dynamics platforms, as have I. I've been doing system dynamics for about 22 years now, 23 years, and I've used probably 4 or 5 different platforms during that time. And I can comment on that. I mean, briefly speaking, I'll say this about system dynamics and AnyLogic. System dynamics and AnyLogic is pretty good. It's pretty well supported in terms of both the basics of defining stock and flow models, and in terms of having those models be able to link in with data, be calibrated, sensitivity analyses, all those sort of basics. But it also is quite good for stratifying models by dimension. So if you have a model that you want to stratify by age categories or by age and sex, you can do that very readily in AnyLogic. And in some ways it compares favorably to some other platforms for that. For example, I'd say it's a bit cleaner than in Benson for stratification, which is, in my mind, the sort of best competing platform. PowerSim would also be up there. I would say that AnyLogic has a real leg up in the sense that the models that you build in system dynamics, because they can be integrated with and closely worked with and even incorporate non-system dynamics features, be it discrete event modeling or agent-based modeling, you have this extra flexibility that you don't have in those packages, and that is something we've exploited to great effect in certain regards. And I would particularly note our work, for example, combining system dynamics models with particle filtering and with MCMC, which are 2 machine learning techniques. We rely very heavily on AnyLogic's extensibility, and it's a beautiful thing. You can do it so much easier than you can in other packages. And in general, if you're doing something a little bit out of the box, I don't know, trying to use it in a GIS context in some way, AnyLogic's going to be so much easier than doing it on one of these other platforms. There is, in my mind, one big shortcoming of AnyLogic in system dynamics space, and it's the elephant in the room, and they haven't yet dealt with it. I still view it very favorably, but they need to deal with this, and that is in VenSim or PowerSim or iThink or Stella from High Performance Systems, these other implementations of system dynamics, one really nice feature is you can run the model once, and then you can go browse to what different variables we're doing in that run. So after the fact, you can kind of look, what did this variable do, that one over time. And it's very powerful. And you can go back to a run you did 2 months ago, and you can kind of compare how that responds to your current run, and you know, get some understanding of that. AnyLogic does not do this, and what this means at a practical level is that if you're going to run a system dynamics run, you need to anticipate ahead of time what variables you want to see as output. That's one option. Or you've got to save enough data away that you could go back and recreate that, you know, export it to R and do the graphs in R or what have you. Use AnyLogic as a sort of solver mule. It solves it simulates it out, and then it exports it to R and you graphics in R, which is okay. But I really think the AnyLogic is missing the boat right now for not supporting this kind of exploratory work with system dynamics models more effectively in terms of saving away results and allowing you to browse them. I think in general it's the leading platform compared to others. in many respects. I think it's light years ahead in terms of several other aspects of its work. But I think this is one area where I feel the pain. And so, if I were to choose a platform right now for a system dynamics model, for the most part, I'd choose AnyLogic, but there are the occasional times where I'll choose Vensim. I have to say, Vensim models are just visually done a little bit nicer, more nicely. They're just a little bit nicer to look at and to kind of interact with. But this is something I could go on for, probably for an hour or two, just to sort of talk about the trade-offs. Those are a couple brief comments, and if you're interested in more specificity, I could show you. Oh, one other thing I would say about AnyLogic, a big warning sign, flashing warning sign. So we have been converting our models from Vensim, system dynamics models, from Vensim to AnyLogic for a number of reasons. Some of those I've just mentioned. And in the process of conversion, we have discovered that AnyLogic's conversion machinery from Vensim to AnyLogic is pretty good in general, but it breaks down for certain subscript features. So if you have a model in Vensim that uses lots of fancy subscripting, don't expect a smooth import into AnyLogic. Expect quite a bit of fix-up. We have lots of experience with this fix-up, and we'd be glad to share it, and we'd be glad to counsel people on how to do it. It's not to say don't do it, don't import it. It's just you got to look for certain characteristic failure modes where it does not thrive. It exhibits a failure to thrive. Import it. So that's something to be cautious about. But in general, I'd say AnyLogic for system dynamics, pretty good, has some rooms for growth for sure. Okay? Yeah. Any other questions? These are great questions. Okay. Do you want to get started? Okay. Okay. So, ladies and gentlemen, we will now stop our initial recording and